Section 4.2 regarding the mean value theorem for derivatives. So in class we did discuss the first page of section 4.2, but I will explain the first page again because there were some people who are not in class yesterday or on Monday. So we did extreme value theorem in section 4.1, where we were looking at absolute values, extreme values like absolute max, absolute min, local max, local min. And we also looked at situations where the derivative was zero undefined and how usually we could find some local max or local min values there. So this is going to be a little different. And you'll see why this theorem actually takes on the name mean value theorem. So let's say I'm driving a Lamborghini. Not really my favorite car, but that's fine. I wouldn't mind driving one. Say it starts at rest. And if you're starting at rest, and let me get my stylus going here. So you're starting at rest, that would be t equals 0, and your position, we'll say it's also 0. Or you can think of it as 0, 0. And within 5 seconds, I travel 330 feet. So we'll treat that like 5, 330. So if I ask to find the average velocity, that's like average rate of change, which we have seen before. And you can think of it like a slope, where we do f of b minus f of a over b minus a. So in this case, if I find the slope between 0, 0 and 5, 330, it would be 330 minus 0 over 5 minus 0, which would just be 66 feet per second. So that would be my average velocity during this 5-second joyride I'm having with this Lamborghini. Just to kind of put this in context for everyone, 44 feet per second translates to about 30 miles per hour. So 66 feet per second would be about 45 miles per hour. But we'll stick with feet per second for this problem. But just so you know, that'd be about 45 miles per hour. So here's the question. Will there ever be an instant during that journey when the actual velocity is this value? So when I start from rest and after 5 seconds I travel 330 feet, will somewhere along the way will the speedometer say 45 miles per hour? Or I guess, for the units I'm using here, 66 feet per second. The answer is yes. And we'll take a physical explanation, but then we'll go and talk about the theory behind this. But if you do step on the accelerator on a Lamborghini and you're trying 330 feet in 5 seconds, I'm almost certain that by the time I've been in the car for 5 seconds, the speed's going to be higher than 45 miles per hour. So I must have passed 45 miles per hour somewhere in that 5-second interval. But we'll also talk about the theory behind it and why that has to make sense, why my actual velocity had to have equaled 66 feet per second within that 5-second interval. Or similar question. Let's say Mr. Reyes, who's not as fast a driver as I am, but say he has a Ferrari, which actually I think is a nicer car. Say he travels 130 miles in 2 hours. And let's say he's leaving from San Jose to like Sacramento, which is usually about a 2-hour drive without traffic. And it's about 130 miles, I think. Well, his average velocity would be 130 over 2. And make sure you have your units. So it'd be 65 mph. Now, will there be an instant when a speedometer does reach 65 miles per hour? Absolutely. That'll definitely happen. So this leads us to the mean value theorem. So the mean value theorem states the following: that if you have a function that's continuous on a closed interval from a to b, so a and b are included in your domain, and if the function is differentiable at every point in the interior of your specified domain, of course not including a and b because usually at endpoints we tend to have things are not differentiable, then we can say with confidence that f prime c equals f of b minus f of b minus a. Now think about this. This is the average rate of change. Or for the couple examples I talked about, the Lamborghini and Ferrari, the average velocity. F prime c will be the instantaneous rate of change, which we know as a derivative, or slope of a tangent line. And so what this is basically saying is that there's at least one x value in your domain where the instantaneous rate of change equals average rate of change. They'll happen at least once. So going back to the example with Mr. Reyes, if he's traveling from his home in San Jose to Sacramento, and his average velocity is 65 miles per hour, he's probably hit 65 miles per hour a few times. And maybe he went a little faster and he's on Highway 5, maybe he had to slow down a little bit when there's traffic, maybe he had to stop for gas, whatever. But, his instantaneous speed, or sorry, instantaneous velocity, or his, you could think of it like, I guess, a derivative of his position function, if you want to call it that, has to equal the average rate of change at least once. So if his average speed is 65 miles per hour, somewhere along that trip he hit 65 miles per hour at least once. So that's kind of the theory behind this. Let's look at this graphically. So let's say I plotted my position with time. This is now going back to the Lamborghini example. And say I connected the points O and A. And let me draw that a little better. So let me connect the points O and A. Now that's a secant line. Remember, a secant line is a line that passes 2 points in a curve. The slope of the secant line always represents the average rate of change. Average rate of change. Which makes sense because average rate of change is f of b minus f of a, right? Or in this case, we're doing 330 minus 0 over 5 minus 0 to get to average rate of change. So the slope of OA is what we calculated earlier in this lesson. 6 feet per second, that's the average velocity for my 5-second journey in the Lamborghini. Now, a velocity, instantaneous velocity line, or if you were to draw a tangent line representing the instantaneous velocity, would be right here. So that's a tangent line, right? Will there be a tangent line that has the same slope as the secant line? Absolutely. Remember, the slope of this line is the instantaneous rate of change. We could definitely imagine this happening. If I drew the secant line, will there be a tangent line from O to A that will have the same slope as the secant line? And definitely will. So there'll be at least, this is the geometric interpretation of the mean value theorem, or MVT, at least one x value in A comma B where the tangent line is parallel to the secant line through A comma f of A, which would be one of your points, so it would be one of your endpoints, right? And B comma f of B, which would be your other endpoint. And those are endpoints we used, to give the formula for average rate of change, f of B minus f of A over B minus A. So we count that happening, because when they're parallel, they have the same slope. So if we look at another example, so like let's say I have these 2 points A and B, and I connect these 2 points. So again, I draw a secant line here. definitely have a tangent line. They'll have the same slope, it'll be parallel to the red line right here. And we said at least once, so it totally could happen 2 times. And we can see how the curve, kind of decreases, then increases, and decreases. So that's why we could get, it could happen multiple times. That the tangent line has the same slope as the secant line. So here's A, here's B, here's C1, and of course here's C2. So now let's try an example, because we talked about that there's an x value C, when we use f prime of C, or at least one point C in that interval from A to B, where the derivative at x equals C equals average rate of change. But how do we actually find its value? So let's look at an example where we can do that. And here we'll look at example 1. So the first thing we're going to want to do is we want to at least show that the function satisfies MVT before we get carried away with this. So for part A, which I'll do right here, if you think about the graph of cosine x, that's a graph that we've seen many times. Kind of looks like that, right? What if I just focus on that portion right there? So here x is 0, here x is pi, and of course that's pi over 2. And that's 1, and it's at -1. Now, the inverse is when you switch x and y. So you want to focus on a portion of the cosine graph that's a one-to-one function. So therefore, your inverse function is also a function. Because remember, for an inverse to be a function, you have to pass a horizontal line test. And we do have some points here that we can look at, like 0, 1, pi, -1, and of course, pi over 2, 0. So the inverse function, if I try graphing inverse cosine x, is when we just simply switch x and y, reflect part of our graph over the line y equals x. But if I just take the 3 points I just labeled and did 1, 0, and -1, pi, and of course 0, pi over 2, because I'm switching x to y coordinates. The inverse cosine graph looks like this. And actually, my curvature is a bit off. Let me undo that. It should look more like this. So definitely it's continuous. Definitely continuous on -1 to 1. And that should be a bracket there. And differentiable in the interior of -1 to 1. So MVT applies. So what this is going to mean is that if I draw a secant line through my 2 endpoints, I should expect a derivative value, the value of derivative to be the same as the average rate of change, or a tangent line have the same slope as a secant line. So let's look at part B. So part B is asking us now to find each value of C and -1, 1 satisfies that equation. Well, let's first do the average, and again, remember that's the average rate of change. We'll let A equal -1 and B be 1. And of course that will be the derivative. And our job is to solve for the x value so that the derivative equals the average rate of change. So, kind of put it more simply, we want derivative to equal average rate of change. Well, let's find the average rate of change. So f of 1 minus f of -1 over 1 minus -1, which will be 0 minus pi over 2. So we get -pi over 2. which makes sense. It's about negative 1.5. If I did try drawing a tangent line, secant line between those two endpoints, it looks like it has a negative slope, about negative 1.5 something. So I think that makes sense. Okay. Oh, that was weird. I wonder how that happened. Oh, there we go. Okay. So now let's find the derivative. So f prime x, remember for inverse cosine, this will be the formula. So it's important you memorize this stuff. That's why we had that test on all the derivative stuff about a week ago. Or if you replace x with c, f prime c equals negative 1 over root 1 minus c squared. And we replace x with c just so it's not confusing, so that it looks like that we're actually trying to solve for a numerical value, not keeping the derivative as just a function or as an expression in terms of x. So this has to equal this. These must be equal, because that's what MVT is saying. So we'll send equal to each other. Negative 1 over root 1 minus c squared equals negative pi over 2. Cross multiply, negative 2 equals negative pi root 1 minus c squared. Divide both sides by negative pi. The negatives will cancel, so you have 2 over pi equals root 1 minus c squared. Square both sides, you get 4 over pi squared equals 1 minus c squared. If you isolate c squared, you should get 1 minus 4 over pi squared. So c would be plus or minus root 1 minus 4 over pi squared. So that's what c equals. Or we could think of it as plus or minus 0.771. So what we'll do next is we'll now try to find the equation of the secant line that passed through A and B. And then we're going to find the equation of tangent line at x equals c, or 0.771 and negative 0.771, and graph it and take a look at all of it. So I'll go ahead and pause the video, and I'll return to this point in the second part.